speak about the introduction to soil mechanic. Last time, I'm not sure how many of you have been on the last time lecture. We spoke about some general stuff about geotechnical engineering, and we are just like moving forward. So we are going to speak about soil mechanic today. We're going to make some just basic stuff about soil mechanic, and then we will advance from it to like some advanced calculations, some the lab tests, and some modeling. I'm going to show you how to model some stuff, how to calculate some stuff. But first, we need to like cover some basic stuff before we move to something more complicated, right? So I'm not sure how many of us of you have anything from the mechanics in general, and I don't know. I'm not sure how many of you deal with the soil mechanics before. So we'll start from the base. So we'll catch up with everything. So for the start, just a bit of interactions. Soils are always the most complex engineering materials, and we are using them from the start of the time. Basically, we did like last time we spoke about how we used to use them for the retaining walls, for the flood protection. We used it like dams before, like air dams, and for the shelters. So Romans actually have like a huge credits for the recognition of the importance of the soil stability structures. So
Seems like the presenter has connection issues. Let's wait for him to reconnect.
sorry for interruption. I just got kicked out for some reason, and we are getting back. I hope that everything is good now. So, as I said before, the Romans have a huge credit for the recognition of the importance of the soil related to the stability of structures. You know that Romans did a lot of stuff like before the tourist period, like aqueducts and the Colosseums and all those stuff that required a lot of engineering. And the Roman engineers, especially Vitruvius, who served during the regime of the Emperor Augustus, the first century before the Christ, actually paid a lot of attention to the soil types. He actually separated the first types of soil, like a sand and gravel, on a silt and a clay that we still use. You'll see after this. And he did some design and foundations. Of course, they haven't been like real theoretical basis for it. It was like mostly based on experience. And then, of course, like with experience, we learn some stuff from it, and then we just learn from mistakes, and we just basically learn from mistake and do something else. So just like some stuff popping out. So the huge name in the soil mechanics is actually Coulomb. Coulomb is a French guy who did a lot of investigations for the physics and for the soil mechanics as well. You will see after there's like a more Coulomb failure criteria that we are still using after like 200 years that happened. So he's actually the first person to use rock mechanic or soil mechanic to solve soil problems. He was a member of the French Royal Engineers, and they did a lot of design for the fortress. You know that period was like plenty of war were happening in all Europe, so we use like a lot of fortress, and to actually like keep ourselves from the enemies that are coming. And that fortress, of course, like required some engineering there. So what he done there is he used to put like a soil like after the fortress wall. So only thing that enemy can do is actually to build a tunnel like beneath the soil mass, and that's of course they become like easy target. And in general, there's like a lot of engineering stuff coming from the war and the military. So it was like that from the start of the humankind. And the mass of soil appeal the lateral force to the fortress that could cause the topple over and could cause some slide away to the soil mass. We will see after we will speak about retaining walls and everything. And when you have a retaining wall, you basically design a retaining wall so you can keep the soil like beneath the retaining wall. And of course, you build a wall because the soil want to move by themselves. And soil, as it is, make pressure that's called the lateral pressure on the walls. They need to calculate the lateral pressure of the soil so you can design the wall retaining structures. So what Coulomb would find is he attempted to determine the first lateral force so he could evaluate the stability of the fortress, and he made the wedge of the soil. The ABC wedge you will see on the next slide is going to be like a bit scheme, and the wedge would fail along the slip plane, and this wedge would push the wall to topple or to move down the slip plane. So what's happening there is this. Just going to put some laser point. So movement of the wedge along the slip plane would occur only if the soil resistance along the wedge were overcome. That's the some basics of the soil mechanic. If you're going to have yes, Charles, I saw that you raise a hand, so please continue. If you have a question. Okay, if you have a question, you can also type in the chat so I can see, and then I will answer you. So like usually when you to have failure, you need to overcome some forces. We call it like a shear force or force of the resistance, and that's something that Coulomb find like really early in the 19th century. And Coulomb assumed that the soil resistance was provided by the friction between the okay, there's two raised hands. So please, if you have a question, you can ask me now.
Seems like Charles doesn't have a microphone, so let's go with Longmo. Sorry if I pronounced it wrongly.
Okay. If I have some issues, you can just type it in the chat, so I can see it, and then I will answer the questions. Like you can ask him anytime. So good.
Yeah. Good afternoon, sir.
Okay.
Yeah, this is Franklin from Cameroon. Okay. I wish to please, if you could help us with study, will be of great help to us.
Sorry, I'm not sure. Do you have problem with connection, or I have problem with connection? So you're bet like
Yes, I couldn't hear his question. Can you repeat, Franklin?
Thank you, Ma. I was pleading if at the end of the presentations you could help us with the soft or hard copies of your presentations for further studies.
With copies of presentations?
Yes, sir.
Yeah, I think I can do it. That's more question for Antonella. I already sent the presentation, but if you want, I can just put a copy in the chat if that's okay with Antonella.
All right, thank you very much.
Yes, of course.
Okay, sounds good. By the end, I will like have the question and everything, and I will put presentation here. Thank you. So back to the Coulomb, and the Coulomb assumed that there's like a soil resonance, what was provided by the friction before between the particles. That actually came true after this absorption, because in the soil we will define now for the more Coulomb failure law, we will define the soil strength by the cohesion and the friction angle, and the friction angle are actually coming from the friction between particles. So he analyzed some of the physics of the mechanics of the wedge failure, and he defined the failure criterion for the soil. And today, the Columbus failure criterion and the method of the analysis are still there, still using for some simple models we have with the soil and the slopes, and even with the rocks nowadays. If you have like some really simple problems. So the thing is, you have a it was fortress back today. Today's they're like retaining walls, or usually gravity walls. Depends what you need to support. Have soil. After that, retaining wall and the soil makes a pressure on the retaining structure. So your job as engineer is to make this wall good enough and big enough and reinforced enough to hold this wedge here that can occur. Basically, there's few things that can happen here. First is like sliding surface on the right side if the slope is too inclined and the strength overcoming the resistance of the soil. And another failure is on the left side, where you can have wedge, and that wedge failure needs to be held by the retaining structure. And that's basically what we're going to do. We're going to first cover some basics and learn how to get parameters and learn how to actually calculate the lateral forces and how to calculate the retaining structures. So let's move forward. Last time we already spoke about Karl Terzaghi, Austrian guy born in Prague, Czechia. He's one of the most famous people in soil mechanics. And we call him the father of soil mechanics. He was a mechanical engineer back in the day. He has a degree in mechanical engineering, and then he decided to move to the geology and the soil mechanics. And the early 20th century, he published the first book related to the soil mechanics. That book is called Erdbaumechanik. It's the German book, and that's the first time when someone actually define some engineering parts for the soil mechanics and for the soil in general. And he actually made one laboratory test equipment that we are still using. We were going to speak about the laboratory test step by step in the next lectures and what to get from those tests. And he actually that was the first time when the theory of consolidation actually was introduced. This is just some equations from the consolidation theory that he made back in like 150 years ago. This one is for settlement, and this one is for pore pressure. And I just leave it there so you can know what he actually did like 150 years ago, so you can feel how complicated stuff there already have been like 150 years ago, and imagine what we have now with all those advanced softwares. So he also defined the soil mechanic. The soil mechanic, also called geotechnique, as French would say, the geotech or the geomechanics is the application of engineering mechanics to the solution of the problem dealing with soils as foundation, as construction material. Engineering mechanics is used to understand, interpret the properties, behavior, and performance of the soils. So soil mechanics is a subset of the geotechnical engineering. which involves the application of the soil mechanics, geology, hydraulics, and the analysis of design of the geotechnical systems, such as dams, embankments, tunnels, canals, waterways, foundation for bridges, roads, building, and the soil waste disposal system. Every application of the soil mechanic involves uncertainty because of the variability of the soil, their stratification, composition, and the engineering properties. So it's basically like a partial solution to the problem. So for the soil mechanic, of course, now we have like a really complex models that takes in account a lot of different parameters. But we'll see, like later we'll speak about advanced soil mechanics, and it's not like it was 100 years ago, of course. But still, the soil is really hard to feel what is going to be behavior of the soil, because like most of the models from the 20th century would just say that soil is a isotropic material, is a homogeneous material, and if we put load, it just deforms in the same axis as you put load in. It's not true, and it's anisotropic, it's a heterogeneous, and you have a bunch of problems with the soil. Because of that, soil is one subject that we are going to like research by the end of the humankind. So what you actually can do? What you can do is like put more pressure on the soil investigations, put more effort in a lab testing, and be sure how you're defining the soil parameters for your design. You're not going to take any parameters that you got from the lab, because the lab sometimes can got the wrong results before some stuff. We'll speak about the lab tests and lab results in the next lecture. And you need to gain some experience, of course, and you need to feel how to actually define parameters, what parameters you need to take. And the most important thing that investors hate is that stability should never be compromised for economy. And you cannot save on investigations. You cannot save on designs. In general, depending on what structure are you building, the geotechnical investigations should cover around 1% of the whole budget for the building. Or for the more complex stuff, for the tunnels and the dams, especially for the dams, it should be like 5%. So you should never be compromised for economy. And because like if you have unstable structure, it's not just that you're going to collapse the structure you build. It's more that you're going to kill someone. That happened before, and it's not fun. It's awful. So there's like always the lessons we are learning for the failures, and those are our best lessons. They're like some of the lives were taken because of those lessons. That's just how it is, especially in the past. Now it's like getting a lot better. Now we don't have that much death injuries on sites. In previous, the tunnels were and the mines were the most dangerous place to work. It was like on every 200 meters of the underground mine, you would have one death. Now that's like 1 in 3 kilometers. So that's still better, but still not perfect. And we work a lot, especially as geotech, we work a lot to prevent anything that can injure someone or worse, kill. So what we have learned from the failures is what got most to us. So all the structures that are founded on the earth rely on the ability to design safe and economical foundations. Because of the natural varieties of the soil, failure do occur, of course, and some failures have been catastrophic and have caused severe damages to lives and property. Other can be just insidious. So failure occurs because of the non-integrated site and soil investigations, some soil and water conditions that you couldn't recognize, some natural hazards, some poor engineering analysis. That's on you. Design, construction, and quality control. The quality control is also in geotech engineers. But sometimes it's not up to you. Sometimes it's really hard to see because it's happening before the natural hazards. It's happening because of hurricanes. It's happening because of earthquakes. Sometimes you cannot see all the stuff that could happen. You can just try to prevent it with as much information as you have. So we spoke last time. We also spoke about some failure we had in history. This is the one of the earliest soil behavior failure that we actually know, that we actually investigated after. Last time we spoke about the tower in Pisa and how we had settlement on the one side of the tower because of the soil, soft soil on one side and stiff soil on another side. That's also one problem. We did a lot of investigations. We understand how it happened. So there's a Trascona grain elevator built in 1913, and it was made to load the grain in elevators, of course. And after 24 hours of the loading, the rate of the loading is about 1 meter of grain height per day. And just after the first day, the bin house began to tilt and settle. Fortunately, the structural damage was minimal, and the bin house was later restored. The thing is, no boring were done to identify any soils to obtain information of their strength. Rather, they did the open pit about 4 meters deep, and foundation and plate was loaded to determine the bearing strength of the soil. So this was like a long time ago. Of course, but the thing is, still with the investors, you're going to fight about the soil investigations, and you need to be really safe there, and you need to know how to decide when to do boring, when to do when the open pit is just okay, and when geophysics are still just okay. So the thing is, this is the big structure. So you see 1, 2, 3, 4, 5 floors there. That's 15 meter plus those foundations, like a 20 meter structure. Usually, if you look, you need to look in the standards and the norms from your country. But in the European Union, we have something called Eurocode 7, and Eurocode 7 define what is the minimum investigation you will have on site. The minimal investigation for the buildings is to have one borehole in a square of 15 x 15 meters, and that borehole needs to be 3 times length of the width of the foundation that's going to be there. So basically, if you're going to have piles that are a meter in wide, you need to have at least 3 meter boring. After you pass the piles length, if you have mat can be like a 20 meter mat in width. You need to have like 60 meter of the borehole, and that's good thing because we have laws for it. So the investors cannot do anything about that just because of laws. So you can get like really good data, and those things are not going to happen in the 21st century, for sure. So also what we do when we have failures, that's when we do reinvestigation for the research purpose. And they did the same thing for this grind tower we mentioned, and they wanted to verify the theoretical bearing strength. So the Peck and Bryan and the Skempton is one really famous guy. You will see a lot of his name in this course in general, but in general, if you're going to read anything about soil mechanics. just have something in the chat. Okay, sorry, just reading the chat. Peck and Bryant found out that the applied pressure from the load imposed by a bin house and the grain was nearly equal to calculate the maximum pressure that soil can withstand. So that was issued with the soft clay soils. The thing is, if you remember what I said before, that was just 1 meter of the grain, and it's supposed to be 15. So it's a good thing that that you can actually see the settlements and you can stop it for the structure like this. But the thing is, if you have something that you have like rapid load on it, or we call it dynamic load, you cannot see it. You cannot save the structure. You just can watch it failing and then go to court because of it, because of your decisions. So we learned that from this failure, the importance of the soil investigations, soil test, and the effect of the rate of loading. The rate of loading is one thing that we are going to speak about a bit later. That's something related a lot for the consolidation theory we spoke earlier from the Carter-Sagi. And especially, that's really important, especially in soft soils for the buildings, and especially for the really big embankments. So we came a long way in understanding soil behavior since the founding of soil mechanics from the Terzaghi, and we continue to learn more daily through research and experience from failures, and your contribution to understanding soil behavior is needed. So it's really important to actually publish what you work on. That's not going to happen like in your early career, but like after 2 or 3 years, 5 years, you will start publishing stuff, and you will understand how important it is, because the more we have data, is we can make stuff more secure, and that's so like in your later career, please try to publish as much as possible. So we are going to continue our journey of learning the fundamentation of the soil mechanic and its application to particle problems, so we can avoid failures or at least reduce the probability of their occurrence. So composition of soil. Last time on the lecture we spoke about how soil is forming. So soils are formed from the physical and the chemical weathering of the rock, and physical weathering involves reduction of the size without any change to the original composition of parent rock. The main agents responsible for the process of the exfoliation: unloading, erosion, freezing, and thawing. The chemical weathering causes both. That's a reduction in the size and the chemical alteration of the original parent rock. The main agents responsible for the chemical weathering is the hydration, carbonization, oxidation. Often, chemical and physical weathering took place in a concern. The soils that remain on the site after weathering, we call them residual soils. Their soils retain many in the elements that compromise the parent rock. The truth is that we don't have much of the residual soils because we have a lot of moving on the earth. On the right side, you can just see how the soil is forming, like on one picture. So you have the parent rock. There we have a little bit of the weathering, and the last step is the soil and the organic soil as you know, like a humus and everything. So we have like a lot of type of soils. Paul, you can ask question.
What do you have to say?
Sorry?
Yes. Thank you for the presentation. I was burning with a question, and I didn't want you to go to the next slide without me asking this question. And I hope you can hear me.
Yeah. Continue.
All right. There is the previous slide.
Okay.
No, the other, yeah, this one with the
This one.
yeah, this one. Now,
Okay.
I wanted to ask because I asked in the chat section and I wasn't answered, so I thought I should just go ahead and raise my hand.
Okay.
You see, with the building tilted, I wanted to know, is this a failure to study the soil composition that made this structure to tilt, or is it a poor foundation construction by those who put it up?
Okay. Sorry for not answering from the chat because I was focused on the presentation. Yeah. So there is not such a thing as a poor foundation. There is just poor foundation design. And the thing is, you need to design your foundation based on the properties of the soil. So this is of course a poor design of the foundations. The thing is that happened like in previous century, so they didn't have a lot of information about it. But in general, that's why I spoke about the importance of the soil investigations. Your main quest is to do soil investigations. There's no such thing as a bad soil. Of course, there's awful soils you need to build on, but there is no soil that you cannot build on. It's just question about design and how much money client can spend. So what you can do here to prevent something to happen like this is that you're going to make good soil investigations. That's why I spoke about norms we have in European Union. You need to recheck what kind of the standards you have in your country, and to see what are the minimal requirements for the investigations. But truth is, this is a relatively big building, so for sure you would have the borings here. The investigative borings is basically like a hole you drill in a ground, and you took samples. You took samples from that hole, like continuously sampling, and then you will do something called the classification of soil. We'll speak about that like in 4 slides, and then you're going to take samples, and usually you take samples on the place where you expect that your foundation is going to be. Like you will get that feeling on with your experience. So you can imagine that foundation is going to be at 1 meter, and you know that that someone already desired that you're going to have like a mud foundation, and then you took sample like right beneath of the foundations, and you took some samples like in more depth, because the influence of the foundation, like stress influence, is 3 times width of the foundation, or if it piles, then it's 10 times. So if you have 1 meter pile of the width, you have like 10 meters of the influence of the load. So that's some stuff you need to understand first before making decision where you're going to take soil samples, and also you're going to take soil sample just before the foundations, if in question, just in case that you're not going to have like deep construction pit. So it is poor foundation design, that's for sure, because if something's failed, it's up to engineer. That's what engineers are going to court. But also happened a long time ago. You cannot let something happen like this today. But you have all the available stuff you can do here to prevent it. So we'll speak about soil investigations. Like one lecture is going to be just about soil investigation, how to get samples, where to do investigation, how to decide what kind of investigation we are going to use, what kind of in situ investigation there is, especially for the huge buildings, for the skyscrapers, for the dams, for the tunnels. But yeah, basically there cannot be bad soil. There can only be the bad investigation and the bad engineering design. So that's basically it. I hope I answered your question. I have some other raised hands, so please continue. Someone else want to ask a question?
Hello? Yeah. Thank you very much. You have been giving us a good exposure. One thing I want to clarify and ask you at the same time. Obviously, soils have very complex structures, and it has, for example, chemical, physical, mechanical, geological, all this descriptions goes to the soil. Now, when you are talking about this wall, are you talking soils with, for example, chemically in the acidic side, which means less than 7 pH, or you're talking about the above 7 pH, which is calcali, or which one you're talking about? When the soils have, when they are acidic, it has structure, chemical structure different from the above the 7 pH.
Okay, so for the designs, the most important stuff is mechanical properties of the soil. So as cohesion, as the friction angle, as the modulus of elasticity. The chemical properties are really important when it comes to the interaction between the structure and soil, because like if you have acid soils can make damage on your concrete if you're using just like a plain concrete as you use for like for every day. So basically, yes, I speak about soils in general because I'm mostly focused on the mechanical properties, because that's something you use in design. But chemical properties, especially, it's easier. For example, Eurocode related to the concrete. There's one norm called 206 related to the concrete in general. There's one thing called classification of the concrete of aggressivity on concrete. So one parameter is the water that is interacting with concrete, and another one is the soil that's interacting with concrete. So if you have fear that your soil can be aggressive, you just do some tests. That's chemical test, and then based on those tests and based on what values you get, you actually just put soil in one group, one category. So then you know how to design your concrete recipe, so it's not going to be damaged because of the soil aggressivity or the water aggressivity. But also, what you usually have is isolation between soil and a concrete structure or the structure of any kind. But also the really important thing about soil and the chemical composition of soil is that depends a lot of the parent rock, that soil from where it came from, basically. So that's the reason why you want to have like a geologist on the site just to see what kind of the rocks there are. One important stuff related to the chemical compositions of soil is that different minerals in the soil can have a lot of effect on the soil behavior. For example, if you have natrium-rich soils, then soils are usually the swelling soils. And problem with the swelling soils, of course, they swell, and you need to decide what kind, you need to overcome that swelling pressure. So basically, last year I worked on one design related to the swelling soils. We had swelling pressure that was like 20 tons a meter. a square meter. So 20 tons of pressure on soil, from soil on 1 square meter. So you can imagine that you can put structure on that soil, like 2 stories structure, put water in the soil, and soil have enough force to lift the structure and actually damage it. So that's the reason why the chemical investigation of the soil are really important. And that's the good way is to actually have the geologists on the site, to have the feeling about what kind of the parent rocks they are. If you have any minerals, or you know that your rain is acid, your water is acid, you know that your water have some artificial the minerals in it, that it's polluted or something like that, then you do the chemical test. And in general, you would do it like for the most of the structures. But you need to have like feel to know where you are geologically, and there's like, is there a chance that you have like a aggressive soil? And then you can actually tell investor, okay, I have concern that this may be aggressive, and we need to do tests so we can protect our concrete and protect our structure. And also have the feeling about soil mechanical properties, because there's possibility it will swell or it will shrink. So that's, I think, I hope that I answered your question.
Thank you very much. Yes, thank you. Thank you so much.
No problem. So there is some more question. The Bahamas Islands are made from limestones. Therefore, the food security is a major threat because we import 90% of our food. Do you think that soil science will make a major difference to our problem? So the thing is, the country where am I at this moment? Like in general, 80% of the whole world are made from the limestones. It's the most common rock you can find. For food security, it depends on what kind of land you have, because even when you have limestones, sometimes you have like thick soil like above the limestones. It's related to the climate as well. So in my country, the south are the mostly limestones with the karst environment, and we have limestones on the north as well, but we have a lot of rain there, a lot of snow and everything. So we have like a 2 meter thick soil layers above the limestones. So I wouldn't say that is a major threat, because it's more about agriculture thing than the soil mechanic as soil mechanic. So, but I think you can treat every soil so you can get anything from it. So yeah, the soil science will make the major difference, but that's more related to the soils. I'm not sure how to call it in English, but there's soil science related to just to the properties of the soil, like more the chemical properties and more the stuff for agriculture, more stuff for the actually growing something. So this is more about the mechanical properties. It's more for the civil engineers who build some stuff. But yeah, yes. Yeah. But the good thing is, if you have background in geology, or you know some geologists, you can have a feeling about what kind of the chemical composition you're going to have in your soils, and based on climate, you can say how big the weathering layer is going to be and how much of soil you're going to get. But yeah, that's more problem to the soil science, not for the soil mechanics. Yeah, but yeah, it can make a major difference if you put research on it, you can get anything. Next question is good afternoon, everybody. Good afternoon. Is it good topic about agriculture, especially for the Africans? Zerikas is in US. If yes, please send me the. Oh, okay, that's something related to someone else. And Hamida, thank you for the dear and good presentation. No problem. I hope that you're enjoying it. Is there any more question? So you can ask. There's one more raised hand from the Franslin, if I got that right. Your mic's on mute.
Good afternoon once more, sir. Can you hear me?
Yeah, I can. Please proceed.
Okay. Thank you very much. This is Franklin from Cameroon. I wish to find out whether as times change, can there be any change in the soil texture or composition?
As time change, yes. Especially if you are talking about for the soil weathering, having the 30 to 50 years of the period of time is enough to have your soil weathered. It most depends on the kind of climate you are in, and if you have like of course, if you have like of aggressor on soil, if you have a lot of wind, a lot of water there, you have like acid water coming there. If you have like a really turbulent stuff, especially for the tropic part of the world, for the really dry part of the world, when you actually have like the soil can dry and crack, and then you have water, so it gets back together. It's yeah, that for sure. Especially if you have a lot of water, it's changing a lot. So usually when you make designs for the highways, for the buildings, for anything, you may design for the next 100 year or the next 50 year. In Europe, you usually do it for the next 100 year. For the mines, for the underground mines, that's a bit less, around 20 or 30 years, because it's not like entire structures. But yes, that's really good question. And the thing is, when you make design, you usually want to cover your soil as much as possible with structure, and you don't want to have like a open soil anywhere. And if you're making design for the slopes, and it's slopes about the highway or about some buildings, you wouldn't just let the like slope be just soil. You would there's some, especially nowadays, there's some really eco-friendly support for the slopes. There's some like grass bushes that are integrated in the geogrid. The geogrid is the material that you're using to make like slopes more stable. It's basically like a sheet of the material, really thin, 2 or 3 millimeters. It's a grid. It's came from the plastic or fiber. Depends what you want and what properties you need. And you have on the slopes, you would put a geogrid, and you would put like a grass bushes there. So you have like an eco-friendly slope, but secure enough to hold for next 50 years, because you don't want to let erosion. Before that, we used a lot of shotcrete, that's spray concrete, just because you want to have your soils, or especially rocks, covered, because they don't weather. So that was really good question. And yes, you need to cover it.
Okay, sir, please. I am asking this question. This question is related to the most recent collapse of a building that took place in Turkey. I may wish to ask you, as a specialist, whether some investigations have been made to really maybe come out with what actually caused that building to come down, view the advancement, the state of technological advancement in Europe. I don't know if there was some studies made for that place to actually tell us what could really cause a building, or if maybe that building was maybe had a lifespan of about 50 years, and maybe it has already maybe attained its maturity. Why could there not be something like a security measure to maybe remove people that maybe destroy the building to repair? I don't know.
Okay, You're speaking about things that happened during the earthquake or something else? Is it we had like the earthquakes in Turkey last year, and we had like a lot of the damage and the collapsed buildings as well. I'm not sure. Are we speaking about that or like some collapse in general?
Okay.
So basically, it's engineering faults. It's there, especially nowadays. There's not a lot of stuff that even for the earthquakes. Even for earthquakes, you have maps. I don't know what's happening in your country, of course, but and I know that it's like more standardized in the US. There is, and in Europe we have like we have a whole standard for it, and we have like what is the maximum magnitude of the earthquake that could happen there. So you design your structures based on all the data you have. And if you're going to make the study for the like a geotechnical study, that's like a paper you need for every building, there's one chapter you need to cover according to European standard. It's hazards from the earthquake and hazard for the collapse from the earthquake. And there's parameters you need to define. And that parameter is a speed of accelerating waves in a ground. So that's the parameter that you pass to the structural engineers, and structural engineers are making their structures based on what you said there. Thing is that it's already investigated. You have it for the past, like maximum magnitude of the earthquake that's possibility to happen in next 500 years. So you use that one because you want to be safe. And yeah, basically you can predict everything now, like mostly everything. And if something collapsed, that's for sure the engineering fault, for sure. There's no debate about that. It's like just engineering, or even if the client don't want to put money for investigation, it's your fault because you accept to work on the below the minimums. So yeah, it's on you. It's always on engineers. So I have two more raised hands, so please continue with the questions. Oh, you're on mute, so please unmute yourself. There's a lot of noise around you, so.
Okay. Are you hearing me? Thank you.
Yes, but there's like a lot of noise around you, so it's really hard to understand you.
Okay.
I can just write the question, and I'm now on the chat, so I'll just read it. If that's okay with you?
Okay. Shall I mute or just continue? Are you hearing me?
I try to continue, and I will try to.
Yeah. Thank you. Okay. Thank you very much. Thank you, dear Dr. Safet. I'm really enjoyed and very happy with your presentation on the course. I have a question on the transcorner grain elevator collapse. That means failure. So as I see on the screen, the initial failure for the structure will be occurred due to the effects of nature of soil, or initially due to the wind load. I want to identify which is the initial cause for the failure of the structure. Is it a wind load which affects the structure to tilt and then after differentially settle, which will initiate originally the failure for the structure? My second question is, when this structure built, first we have to have a provisional code of construction. Does the construction initiated by using the code of construction, by using the code of construction of the area, by taking the code of construction for the building structure should be considered during the design before execution. So thank you very much for your answer.
Oh, no problem. For the wind, and it's tilted, but I can understand why you're asking that. The wind actually have like huge influence in general on the structures, and huge influence of the like of the moving of the structure. So in general, the rule for the construction is that 1/370 of the height of the building you can have tilted top. So basically, for the Burj Khalifa, the top can move for 5 meters left and right, like normally. Like nothing is going to happen. If you have top that's moved for 5 meters, that's still okay because of the elastic properties of the construction. In this case, no. In this case, no, because the article said that the problem, like re-investigation after that they wanted to see what happened there, they figure out that the load were like next to the limit of the load that soil can take. So basically, you have something called uniaxial strength of the soil, and there's like bearing strength of the soil. That's how much soil can bear, and there's calculation on it. We work on the calculations, how to calculate how much the soil can bear for the different kind of the designs. And what they figure out is that load that they had there is more on the limit of what soil can take. So it basically collapsed because of the soil bearing capacity. So Antonella just said to me that we are by the end of the class. So there's some slides left. There's like 30 slides left. So what we are going to do is we are going to continue with the presentation next time to do some basics, and then we're going to speak a lot about the investigation in general in the lab investigation in general. So there's just one more question I saw in the chat. I'm going to answer that one, and then we're going to be off. So the question is, the study comes in a time where some of the African countries do not use geologists at the start of the construction project. I think more buildings collapse, especially in some cities, needs to be investigated to see whether all the disciplines were involved or the research be done to make clear no doubt on the characteristic of the soils. Yes, it's a big issue in a lot of third world countries, that you don't have investigations, that you have a lot of illegal houses, that you have a lot of places that don't actually have permit to be built there. The people just go there and build because like no one is going to do anything to you because of that. And yeah, there's a lot of problems here as well. In Sarajevo as well, we have a lot of legal places. Thing is, what we're doing now is we're hiring engineers that have like more than 5 years of experience. They check every house like from the start that don't have the permit to be built there. It's a government money, government is paying for it. And after the engineers do the check for the construction side, for the electrician, for the plumbing and everything, they make their decisions. Can that home stay there, or you need to do something with it, or it needs to be collapsed? Also, a part of those engineering inspections are the geotechnical engineering inspections. So if you have house built on landslide, we have it here, we have like 2,000 landslides just in the city, so it's awful. And if you have house built on the landslide, they will tell you what you need to do or how it's going to be collapsed. So that's problem in a lot of countries as well, but there is some stuff like this that you can do actually to prevent it. More questions is in the event one does not know the quality of the soil, which building structure is safe. You cannot know. If you don't know anything about what you're building on, you cannot know if it's safe. You can just pray for it that is, and don't go there. How we can prevent the erosion during the 4 meter of the depth excavation? So usually when we have the like deep construction pits, when you have like a deep excavation, that's usually something we do for the parking lot. You have like -2 or -3. Now we are building one deep construction pit that's -20 meters depth in depth. That's huge. So what you do there is when you do first, of course you do the soil investigation and everything, and based on soil properties, if you have really good soil, it can take like a 4 meter of depth of the excavation, but you need to like made wide opening of the pit, and because you cannot have like vertical excavation everywhere, because it's just going to collapse. We had like 2 years ago, we got like really inclined excavation in the pit, like that was like 3 meter pit, and the worker died because like it was in gravel soil and collapsed. So one person died there. Now they're on court because of those things, and you cannot let that happen. And if you don't have space, that's something that's happening in the cities. You basically don't have space to make it wide. You do some stuff to support it, and those some stuff are the piles, the Berlin Wall, or you can make a wall, the diaphragm wall, and you basically like drill like huge foundations with the excavator, and you pour the concrete, you put the reinforcement and everything, and then you just like dig inside of that wall. So for the piles is the same. Depending on what kind of soil you have, what kind of how deep it is, you're going to calculate it. And the thing is, you need to have it like there's one thing called a safety factor. Safety factor is like this is how much I can my ground support can take. This is how much it needs to take. So usually for the buildings it's 1.5. So you need to like maintain to have 50% more of the strength that you actually need for the phases, construction phases. That's 1.3. So you just need to be sure that's not going to collapse during the excavating. So we usually do the pile walls because it's easier. You just put the machine there, drill the piles, it's gone really quickly, and you just excavate. And if you have like a deeper one, you can like put bigger piles, you can put anchors there, and that's some stuff you're going to model by the end of this course. And I'll show you how it actually works with slopes. Is it safe to say that soil density tests should be done prior to building? Thing is, when you're doing the soil investigation and the lab test, the soil density is one test that you needed. Like for everything you need it. For any kind of the other test, you need soil density because it's really huge part of the calculation. And there's two different stuff. One is the density of the particles of the soil. That's usually 2.65 tons per the cubic meter. And what's the more important stuff in the soil mechanics and civil engineering, in the geotechnical engineering, is the unit weight of soil. So that's soil in the natural state. So how much soil weight in like just like it is. So that's usually like for the soils is 1.8 ton per cubic meter, and if it's saturated, it's 2.2 ton per cubic meter. We'll speak We'll speak a lot about that. We'll speak a lot of about investigation in general, like soil investigation. By the end of this presentation, there's like some like basic calculation of the soil density on the unit weight of the soil, of the porosity of the soil, and stuff like that. But we'll get to it like next time. Is it safe to say that soil density? Okay, I already answered this one.